The next proof technique we're going to look at is something called proof by contrapositive. And before watching this video, I would encourage you to look at the activities on the file called Introduction to Proof by Contrapositive. It'll give you an introduction to the kind of ideas that we're looking at in this video. Hopefully make it a little easier to understand. I will want to be clear that those particular problems will not be on the quiz, but they will help you build some understanding. So we're going to look at proof by contrapositive. We're going to first discuss how we can use logically equivalent statements to help us prove theorems. We're going to define the contrapositive of a conditional statement. We're going to show that the contrapositive of a conditional statement is logically equivalent to the original conditional statement. And then we're going to use that to prove a theorem. Okay, so remember back from our Math 225 days that two statements are called logically equivalent if they are logically the same. In other words, either both statements are true or both statements are false. And another way of looking at that is there is no situation in which one statement is true and the other is false. So suppose you wanted to prove some statement, I don't know, P, and you know that P is logically equivalent to another statement, Q. Well, it is possible that the way that P is stated, it might be either difficult or maybe even impossible to prove. It is possible that it is easier to prove the statement Q because of the way it's worded or because of its structure. The nice thing is, if Q is true, that means that both P and Q are true. Remember, our only two choices is either both P and Q are true or they're both false. That's what it means to be logically equivalent. And we know they can't both be false because Q is true. So if we know that Q is true, that means that both P and Q are true, which means that if we can prove that Q is true, then we automatically prove P is true, even though it is a different looking statement. So let's see if we can play with a conditional statement to find some kind of logically equivalent statement for it. Now, there are at least two ways that we can play with a conditional statement to make it into another conditional statement. So if you have the statement if P then Q, you can do what's called the converse of the statement, which is just switch the conclusion and the hypothesis. If Q then P. You can also do something called the contrapositive, which is if not Q, in other words, if Q is false, then not P. In other words, then P is false. And that's called the contrapositive. Now, I want to note that for both the converse and the contrapositive, those are only possible when you have a conditional statement. If you have a statement that is not conditional, converse and contrapositive don't make any sense at all. All right, so let's look at an example. If you behave, then I give you a cookie. So that's a conditional statement. The converse is I just flip the hypothesis and the conclusion. If I give you a cookie, then you behave. Well, maybe, but who knows? Contrapositive is, well, let me see. So I'm going to take the negation of both the hypothesis and the conclusion and flip their order. So if I do not give you a cookie, then you do not behave. So these are certainly different statements than the original conditional statement, but the question is either of those, or maybe both, logically equivalent? So let's start with our original conditional statement, if P then Q. So this is false precisely when the hypothesis is true, so P is true, and the conclusion is false, Q is false, and otherwise it's going to be true. That's the way I kind of like to understand how conditional statements work. The converse is if Q then P. That is going to be false precisely when Q is true and P is false. And you can already see that's different than when the original conditional statement was false and true otherwise. So that is not going to be logically equivalent to the original statement. It was a good try, but it didn't work out. Let's see what happens with the contrapositive. So remember, the contrapositive is if not Q, then not P. So that one is going to be false precisely when not Q is true and not P is false. And if we can sort of unwind those knots a little bit, not Q is true means that Q is false. not P is false means that P is true. So this happens when Q is false and P is true. Now I wrote that in a slightly different order than the original conditional statement, but otherwise it's exactly the same as what we had before. So that is actually logically equivalent to the original statement. That means that a conditional statement and its contrapositive are always logically equivalent, but again, the converse is not necessarily going to be that way. All right, so let's look at a theorem that is going to be difficult to prove directly, but maybe if we convert it into the contrapositive, we can prove it that way. So again, hard to prove. This one says, let A and B be real numbers. If B is not equal to 0, then either A, B is not equal to 0, or A is equal to 0. And this is going to be a little bit tricky to prove directly, more than tricky. I would say that not practical at all. But let's see why, right? So we're assuming that B is not equal to 0, and we want to show that either A, B is not equal to 0, or A is equal to 0. So that means we got to prove that one of those is true. Now, if you try to prove that A, B is not equal to 0, well, that might not actually be true, right? It might be that A, B is equal to 0, but that A is equal to 0. And you say, okay, fine. What if I try to prove A is equal to 0? Well, then they might switch back and say, well, maybe A is not equal to 0, but AB is also not equal to 0. So every time you try to prove one of those statements in the OR, then maybe that one's false and the other one's true. So that makes it really... So in general, proving an OR statement directly can be very maddening. Let's look at the contrapositive, see if that's any easier to prove. Remember, it's logically equivalent to the original theorem, so proving the contrapositive is exactly proving the original theorem. So we have to negate the hypothesis. Let me see. Our original hypothesis is B not equal to 0, so B equals 0 is negating that. We have to negate the conclusion as well. Now, the conclusion is an OR statement, so when we negate that, we get an AND statement by our buddy De Morgan, right? So negating that conclusion means that A, B equals 0 and A is not equal to 0. And then we flip the hypothesis and conclusion for the conditional statement. So our contrapositive is if A, B is equal to 0 and A is not equal to 0, then B is equal to 0. And already we can see this one, it might be a little bit easier to handle. All right, so our theorem is if B is not equal to 0, then either A, B is not equal to 0 or A equals 0. But what we're going to prove instead is if A, B is equal to 0 and A is not equal to 0, then B is equal to 0. So we're going to assume that A, B is equal to 0 and A is not equal to 0. And then we're going to show that B is equal to 0. So the nice thing about A being non-zero is that taking its reciprocal makes sense. So if A is not equal to 0, 1 over A is an actual real number. So if we take the equation AB equals 0, which by the way we are assuming, and multiply both sides by 1 over A, the A's are going to cancel and we end up with B equals 0, which is exactly what we wanted to prove. So now if we write this up formally, our original theorem is if B is not equal to 0, then either AB is not equal to 0 or A equals 0. And we are going to warn our reader that we are not going to prove this directly. We're going to say we are going to prove this theorem by the contrapositive, which means we are going to prove the statement if AB equals 0 and A is not equal to 0, then B equals 0. We tell our reader what proof technique we're going to use. We tell them what the statement is, the new statement is that we're going to prove, so that they can see the new statement is equivalent to the original. So we are going to assume that AB equals 0 and that A is not equal to 0, and we're going to show that B is equal to 0. And remember, it was important for us to find the multiplicative inverse of A, so we say, since A is not equal to 0, it has a multiplicative inverse 1 over A. Since AB is equal to 0, we can then multiply both sides by 1 over A to get 1 over A times AB equals 1 over A times 0. And we're going to compute those two quantities individually. 1 over A times AB is the same as 1 over A times B, which is the same as 1 times B, which is B. And 1 over A times 0 is equal to 0, and therefore that equation becomes B is equal to 0, and that completes the proof. So that gives you an idea of how proof by contrapositive works. Go ahead and continue that on the activities. The name of the PDF file is Proof by Contrapositive, and it is included with this video.